specifically how to scale a cloud DVR infrastructure. Cloud DVR is actually the big thing happening those days. So I'm pretty sure you have already heard of that, but maybe to start with, we will go through an idea of what it exactly included in a cloud DVR service. And after that, we'll see how that can scale efficiently. Very quickly, brief introduction regarding the company. I'm working for Anevia, which is a company I co-founded about 15 years ago. And prior to that, my student project was a small software that you guys might have heard about. It's called VLC Media Player. And after that, we've created Anevia. Anevia currently provides OTT and IP software for delivery of video services, and more specifically, live TV, near live TV, and video on demand. So let's jump to the topic. What is cloud DVR? So cloud DVR in a multi-screen environment means delivering to multiple screens, starting with obviously mobile phones, tablets, but also game consoles, connected TVs, different set-top boxes such as Apple TVs and such other set-top boxes, and delivering a set of different services. Obviously, the live TV service is something that is quite well deployed nowadays. But the idea of cloud DVR is to increase the quantity of the amount of time that will be recorded in the network to provide services such as time shift, the ability to pause while you are actually watching something, the ability to rewind. Then you have the start over, which is the ability to start a program back from the beginning, even if you missed the beginning. And then we also have catch-up replay, which would be more like 7 days, catching up on all different programs for 7 days. And eventually, cloud DVR, where you can program the recording in the network of a given show and then watch it like months later or even years later because it's been kept in the network. In terms of legal models, we currently have 2 different legal models which apply depending on the different countries, and it's really like country by country. On the one hand, there is the shared copy model, which is the easiest one in terms of technology. It means that it's being recorded in the network and then anyone can access, provided the person has recorded, provided the person has programmed the recording of the show prior to watching it, then everyone can access the same data. This is a shared copy model. In the US and few other countries, there is a specific regulation that requires to have the data for each user and specific data for each user. It's called remote storage DVR because everyone has its own data. So if 10,000 subscribers record exactly the same TV program, the operator has to keep 10,000 copies of that program. As you can imagine, that has a major factor on the way the system will scale. In fact, there are a lot of different models, and we can't say that there's just 2 business models. There is a whole list of what is accepted or not in terms of legal model. I may not go through all this list, but I think it's important to keep in mind that in each country there is some specificities regarding what is possible and what is not possible. So let's try to keep that in mind. Maybe moving to the really different factors to scale a cloud DVR. What's important is obviously the number of channels. A system that records 50 channels is not the same system that records 100 or 200 channels or 1,000 channels ultimately. And then second key factor and second key metric is the amount of time for which you will record and keep the different recordings. Recording for 30 minutes for a post-TV service, or recording for 4 hours for a start-over service, or recording for 4 months for a cloud DVR service. This is very, very different, and that has a major impact on the amount of storage that will be required. And number 3, the third metric in there, is the number of devices that the operator would like to support. Obviously, supporting just one device, like iPhone, is very different from supporting iPhone, iPads, Android phones, Android tablets, Windows phones, game console, connected TVs, etc., etc., etc. Worst case, if you store all those different contents for each user in all the different formats for all the different devices, that is a huge amount of storage required. Last, and the more obvious metric, is the number of users. The more subscribers to the service there is, the more storage is required, the more streaming servers are required, and so on and so on. So that's really the topic for today, is to see what kind of technologies could be deployed in a cloud DVR service in order to minimize the impact of those different factors and in order to make the scaling efficient and smooth. So let's start with the first 2 technologies here, and we'll go through a specific focus on the storage afterwards. First technology is what we call packaging on the fly. Packaging on the fly is really the ability to record a pivot format and package on the fly that pivot format to the requested format. So you have only one asset that is stored and recorded, and then if it's requested by an iPhone, it will be packaged with the right format for an iPhone, which would be HLS, with the right DRM for that iPhone. And if it's requested by a Xbox, it will be packaged with the right format for an Xbox, meaning in that case smooth streaming, with the right DRM for this Xbox as well. And the same for a connected TV, etc., etc. So that way, we just record once, and we can deliver for any kind of device, including potential device of the future that will be requiring some new formats that will be available through just a software upgrade, but without reprocessing all the catalog and without reprocessing all the different assets that have been recorded for the past few years. So that first technology minimizes the impact on the number of supported devices in a cloud DVR environment. It enables scaling the number of devices without having to scale the storage at all. Then, if we look at, let's say, the legacy way of handling cloud DVR, it used to be what we call live to VOD. So live to VOD, what does that mean? Usually there are some servers to record a given buffer and then extract a portion of that buffer based on what people have actually recorded. So typically, if someone has recorded from start time to end time, we will create a specific asset for that person. The limitation of that model is that if you have 2 subscribers that recorded slightly the same, that recording the same show, but with slightly different start time and end time, because someone wants to start 5 minutes earlier and someone wants to end 10 minutes later, then it creates 2 separate assets, and you can't mutualize those assets. So with this technology, when the number of users grows, then the requested size of storage also grows very significantly. An optimized way of handling that is what we call optimized recording, which means actually the server will record some video sequences, like typically 5 or 10 minutes video sequences, and it will only keep the 5 or 10 minutes video sequences that someone recorded, and it will actually delete all the sequences that nobody requested. In that case, with the ability to rebuild an asset from different sequences, then at worst, one single video sequence will be recorded only once. It will be recorded either once or not at all. It will never be recorded multiple times, which is really the point. And in that way, growing the number of subscribers doesn't really grow the amount of storage required for the deployment. So those two technologies are really key to limit the impact on the number of devices and the number of subscribers in a shared copy environment. But let's go now to the storage challenge, because the real challenge of a cloud DVR service is really on the storage. Obviously, as you can imagine, recording a 30-minute of all different channels for, let's say, 100 channels, that's something very different from recording 7 days on 100 different channels, which is also very different from recording 3 months. And what about recording 3 years? And why limit that to 3 years? Maybe it's going to be 10 years, in which case we need to find a way to actually scale this storage efficiently. What's important there is to understand that the different services actually require different kind of storage. So we will try to specify the storage based on 2 metrics. On one side, we've got the capacity, so how much storage is actually involved. And on the other side, we've got the performance of the storage, meaning basically how much data can we read from the storage, how much data can we write on the storage. First, a service like a time shift service, it doesn't require a lot of storage in terms of amount of storage, because for a time shift service, you only record, let's say, 20 minutes, 30 minutes. So this will be a few tens of gigabytes, maybe 100 of gigabytes, but not a huge storage really. However, it requires a lot of IOPS, so a lot of reads, because there will be a lot of users to read a very small amount of data. So this means really a high requirement on performance on that storage. Second service, catch-up or replay service. It requires more storage. It typically requires a couple of terabyte storage, few terabyte storage, maybe 10, 20, 30 terabyte storage with high performance, but not as high as a time shift service. Moving to a cloud DVR in a shared copy environment, then it requires even more storage capacity. We're typically talking about, from half a petabyte to few petabytes in terms of storage, but with lower performance on that storage. And the last one, cloud DVR in a private environment, then each content can be accessed only by one subscriber at a time, so it's very, very, very low performance required. But in terms of storage, typically in a private copy environment, the operators will propose something like 300 gigabyte per subscriber, which if you have 1 million subscribers, makes 300 petabytes, which is a huge, huge storage involved. So this is really the different kind of storage that are required for the different services. Let's look at the different technologies available in the storage area and how they can actually answer the requirements from here. First technology, which is probably the most deployed at the moment, is the network attached storage technology, which we usually call NAS, okay, network attached storage. And basically, that technology, it can fit more or less any performance and capacity requirement, usually not very, very high performance, which is the reason why it doesn't really cover the time shift area, but for any other kind of service, it can be served through network attached storage. It provides a scalable architecture, but the integration of a network attached storage can be sometimes complex, especially from a network point of view, because connecting all the storage to all the different streaming servers through a network can be quite complex. Yeah. So that's the first technology. You can typically deploy things like EMC Isilon, which is probably our best partner to do that, but any other NAS would fit in there. The second option is to use direct attached storage, and that perfectly fits the requirement for a time shift service, because as you can imagine, with direct attached storage, you can't put a lot of storage in each server. You can easily fit few hundred gigabytes. You can probably fit a couple of terabytes, but after that, it becomes quite difficult. So typically for a time shift, that is the right technology, especially using SSD drives that will actually deliver very high IOPS. It's a very easy integration, but in terms of scalability, it has limits, because typically when you try to scale such an architecture, it means adding disks in the different servers, and there is a limit to that. In order to secure the service, then if a server fails, you need to run on a 1+1 redundancy model, which is at some point quite costly as well. So what we've seen more and more coming, and what we now deploy and what we have developed is based on a technology called embedded distributed storage, which means the different streaming servers will all put together their storage capacity that are available inside each of the streaming servers. And when we put all that together, it becomes kind of a virtual NAS, making data available from any servers and recording on a distributed manner around all the different servers. The interesting part of that infrastructure is that it has a very simple scalability, because each time a server is added to the farm, then it increases the storage capacity, and at the same time, it increases the streaming capacity. So whatever you want to increase, you just add a server to the farm, and it will scale the service. And the streaming capacity and the storage capacity, they kind of scale together. The more subscribers you have, the more storage requirements you have, and the more streaming capacity requirements you have. So that last architecture really fits for pretty much all the different use cases with a much more simple integration. If we finish by comparing the different technologies, what we really have are the direct attach with SSD, which is one that will perfectly fit for time shift, Then we have the network attached that will perfectly fit with catch-up, replay, cloud DVR in a shared copy environment, but also for cloud DVR in a unique copy environment. Embedded distributed storage will actually be a good technology to fit all those services. But the interesting point of that technology is that if we look at the space required for such a cloud DVR deployment, in case of a NAS deployment, you will need a lot of different streaming servers to pile up to deliver the required streaming capacity. And next to that, a pile of different NAS nodes to pile up to deliver the right storage capacity. What we estimate is that for an average cloud DVR deployment, in year 4, you need about 400 rack units in order to deliver the service in a NAS environment. So 400 rack units means basically between 10 and 15 racks full of servers in order to deliver that. In a EDS deployment, because the storage and the streaming servers are located in the same machine, in the same server, it basically requires half of those 400 rack units, only 200 rack units, and 200 rack units that fits in 5 to maybe 8 racks of servers. And there's also an equation around the amount of networking equipment required, because when you lower the number of servers, you lower the number of switches, etc., etc. So it makes the integration much, much more easier. So trying to go through the conclusions in order to have a service, a cloud DVR service that scales smoothly, scaling with the number of channels, scaling with the duration of the recording window, so how long you will keep the asset for, scalability on the number of devices, and scalability on the number of users. Then we identified today, and that was what I wanted to share with you, we identified 3 major technologies. The first one being packaging on the fly, so the ability to adapt the content to the device on the fly and not record for each device. Optimized recording, the ability to record video sequences and share those video sequences amongst different users to minimize the number of different assets that are being recorded. And then the last one being the embedded distributed storage, so the ability to use the embedded storage in a distributed manner so that it provides kind of a virtual NAS across the different streaming servers, reducing the number of servers required for a full cloud DVR environment. That's it. If you have any questions, I'm happy to answer those questions. Yeah. Any question, anyone?
So are you storing the data in the cloud generally, or actually in the person's home on their own drive?
That's a good question. I mean, typically here we're talking about a cloud DVR service, so it means somehow for the end user, the data is stored in the cloud. Now, when it comes to how the operator, how the service provider is deploying that, we're seeing 2 different models. Either the service provider deploy the different servers in their farms, in their data centers themselves. That would be for service providers that are used to manage IT equipment. Typically, telco operators, cable operators would rather go that way. And on the second hand, we've got service providers that are more oriented through the content rights that are not used to manage IT equipment. And in that case, they would actually deploy this solution in a what we call public cloud. So typically deploy that in Amazon or Microsoft's Azure and so on. So we see both cases really.
Yeah, okay. One more question. So when you take you're recording the data, I presume you're recording it from the home up to the cloud, correct? So you have to deal with the uplink of the person's home's uplink connection, or do you actually record it directly off a live stream?
Exactly. We record it directly off the live stream. So which is a reason why it either fits, all this either fits inside the head end or next to the head end in a data center connected to the head end of the cable operator. Or we are actually set up a link between this head end and Amazon or whatever so that we can send the streams to Amazon.
I have a question about the packaging on the fly. Is it the same technology as like you doing in the encoder? You provide like adaptive bit rates on the same video, right? So
yes.
It can fit into different devices. Okay.
So it's another technology, but they kind of sit together. So the encoder, what they will do is provide the different resolutions, the right resolution and the right bit rates. So this is typically the ABR technology, adaptive bitrate technology. But then each of the different manufacturers have their own standards. And the standard to deliver a video on an iPhone is called HLS. It's the Apple standard in some way. Whereas the way of delivering a video to an Xbox is called smooth streaming. And that's a standard from Microsoft. It can use exactly the same resolution. It can use exactly the same H.264 encoding, but it's a different transport protocol, okay? So it's a different way to present it to the device. So what we do is not doing the encoding on the fly, it's doing this adaptation to the right format with the adaptation to the right DRM as well.
Yes. So another question about embedded distributed storage. So looks to me like it's similar to the DAS. It's just like you have a multiple DAS solution. So if you think about like the cost, it's actually just like a multiple of a single DAS, right?
In terms of cost, in terms of hardware cost, yes, it will involve the same hardware cost because basically you will reuse the drives that are in the different servers. But the difference is in the scalability model, where if you are using DAS as a pure DAS, then in terms of scalability, the only thing you can do is add more disks in the server. And at some point, it doesn't fit in that server. Whereas in an embedded distributed storage environment, what you do is you are using all those drives from all the different servers and you put them together somehow in the same manner that you put different disks together in a RAID array. You would put different servers together in this EDS array. Okay? So if you need to increase the size of an EDS system, you can add a server. Just like if you want to increase the size of a RAID array, you can add a disk.
Yeah, so in other words, the cost is the same, but you connect it to you make good use of it when there's a lot of those servers.
Exactly.
Okay, thank you.
Okay, any other question? Well, so we are located just over there, SU 11606. So if you want to come by, if you have any question, you will be welcome. And thank you very much.